For the next 30 to 50 years, Indonesia will continue to suffer and remain dependent on fossil fuels. At least, that's what the Indonesia's National Energy Council said. Hello everyone, and welcome to our presentation video. We are delighted to have you here as we discuss an important issue that affects the future of our beloved country located in Southeast Asia, Indonesia's Sustainable Energy Challenge. But before we dive in, you might be wondering, why do we choose this topic? According to Indonesia's National Electricity Company, PLN, in 2020, coal and natural gas accounted for 62.85% and 21.4% of our electricity generation, respectively. This means that over 84% of Indonesia's electricity still heavily relies on fossil fuels. Ladies and gentlemen, this reality stands in contrast to the massive potential that Indonesia has, especially considering that Indonesia has rich water resources. We would have a tremendous opportunity to harness hydropower. Yet, hydropower currently contributes only 6% of our total energy mix, showing that this resource remains underutilized. So, what exactly is hydropower? In simple terms, hydro energy, often called hydropower, is a renewable source where electricity is generated by the movement of water. It typically involves using the kinetic energy of flowing water to spin turbines, which then produce electricity. Hydropower is clean, sustainable, and has been used worldwide for decades. However, traditional hydroelectric dams require large-scale construction and significant land use. This is where vortex turbine comes in as our approach to help solving this problem. A vortex turbine is a decentralized system that generates electricity by creating a controlled vortex, even from a small flowing stream. This is why we believe vortex turbines are particularly well suited for Indonesia's geographical and environmental conditions, which have countless small rivers scattered throughout the nation. Without further ado, Brain will walk you through what exactly a vortex turbine is.
Okay, thank you, Giovanno. Now we get into the question, what is the vortex turbine? We can see some of the example image here. By the definition, the vortex turbine is a type of micro hydropower plant converts energy in a moving fluid into a rotational energy. You can see some of the component here. The first is an inlet channel, which is channel that directs the water into a vortex chamber. It initiates the swirling motion by injecting water tangentially, leveraging the conservation of angular momentum to create a vortex. The next is the vortex chamber, or we can call it a basin, which is the primary structure, typically a cylinder or a conical concrete or maybe metal basin, where the vortex is formed. Its shape and dimensions are optimized to sustain a stable, strong vortex. Alright, the next is a turbine blades, which is a rotor or impeller located in the base and the center of the basin. It extracts rotational energy from a swirling water to drive the generator here. The next is a discharge hole, which is a central hole in the pipe of in the bottom of the vortex chamber, where water exits after passing through the turbine. It maintains the vortex by allowing continuous flow, creating a low pressure zone. The next is a generator here, which is an electrical generator coupled to the turbine via shaft or gearbox. It converts the mechanical energy from the turbine's rotation into electrical energy. Then next is we will focus on the turbine blades itself. So most of the water turbines use vertical blades that are straight and aligned with the axis, which is simple to produce. However, turbine is low in efficiency. So we use curved blades in our vortex turbine here, which is designed to optimize water flow, reduce energy losses, and also improve the energy. And next, how the vortex turbine actually works. Have you ever watched water drain from a bathtub and noticed there is a whirlpool forming as it spirals? That's its vortex, and we just have same principle as a vortex hydro turbine. We can use this as a mechanism. Unlike the traditional hydroelectric dams that require a significant drop in the water level, vortex hydro turbine can generate electricity from the river or the stream with just a small elevation difference. Water will generally move from the river into a spiral basin here. The basin is shaped to encourage the water to start rotating, creating a powerful vortex. And due to angular momentum here, the water will speed up as it moves towards the center of the vortex. And then this concentrates the kinetic energy of the water, making it more efficient to the power generation. As we know, the turbine blades are waiting to capture in the bottom of the vortex. The fast-moving water will hit the turbine blades, causing them to spin rapidly. The spinning turbine is connected to a generator that converts the mechanical energy into the electrical energy. After passing the turbine, the water exits the basin from here and flows back into the river, continuing the wave normally. And what is the advantage of this water turbine actually? We can pass it into my friends here.
Thank you, Brain. I will first explain the mechanisms of three different traditional hydro turbines. First, we have the mechanism of the Pelton turbine. Water is directed through a nozzle, where its potential energy is transformed into kinetic energy, resulting in high-speed jets that strike the turbine's buckets. The interaction of these jets with the buckets causes the turbine runner to rotate, ultimately generating electricity via a connected generator. Moving on to the Francis turbine. Firstly, water enters through a spiral casing and passes through guide vanes, which directs it onto the runner blades. As the water flows through the runner blades, it causes the runner to rotate, which drives a connected generator for electricity production. Moving on to the Kaplan turbine, the water from the scroll casing flows over the guide vanes. Then it is deflected through an angle of 90 degrees in between the guide vanes and runner blades. Then it flows actually into the runner, which causes the runner shaft to rotate. This rotation is then transmitted to a generator which is coupled to the runner shaft. In hindsight, those three turbines might be the best option right now to generate hydroelectric power. However, this is far from the truth, as those turbines suffer from some major disadvantages. So, what are their disadvantages? Let's start with the disadvantages of Pelton turbines. Pelton turbines can experience significant energy loss due to complex internal flow mechanisms and turbulence, which affects efficiency. Furthermore, research indicates that the efficiency of Pelton turbines diminishes due to factors like jet interference, which occurs when the jet does not sufficiently fill the buckets. This inefficiency at lower operational heads restricts the use of Pelton turbines primarily to high elevation sites. Additionally, the traditional metallic construction materials used are susceptible to corrosion under continuous high-pressure jet operation. Next, we have the Francis turbines. Francis turbines, which are typically employed in medium to high flow scenarios, face challenges like significant energy loss due to flow separation and vortex formation as they increase turbulent losses. Moreover, the mismatch between the water inflow angle and the blade's design incidence angle can happen, which leads to shock losses, which further decreases efficiency. Francis turbines are also susceptible to hydraulic instabilities due to vortex rope formation in the draft tube, which leads to significant pressure fluctuations and vibrations. Such hydraulic instabilities can result in extreme mechanical stress that compromises long-term operational reliability, which makes maintenance a recurrent issue. One of the primary disadvantages of Kaplan turbines is their sensitivity to varying flow conditions. While they can adjust the runner and wicket gate angles to optimize performance under fluctuating flow rates, this responsiveness can also lead to inefficiencies when operating outside the best efficiency point. Frequent load variations can exert dynamic stresses on the runner blades, leading to mechanical failures. Cavitation is another significant concern associated with Kaplan turbines. This phenomenon occurs when pressure drops in certain sections of the turbine, leading to vapor formation, which can implode and damage the blades. This will lead to costly maintenance fees and a reduced operational life. Moreover, a disadvantage that all three traditional water turbines have is that they cause the death of many aquatic creatures because of their high rotation speed, sudden pressure changes, and shear forces. Next, I would like to go over the main advantages of the vortex turbine and why it does not suffer the same issues as other popular traditional water turbines. One of the main advantages of the vortex turbine is its ability to operate effectively at low water flow heads, typically ranging from 0.7 to 3 meters. Additionally, the vortex turbine utilizes a whirlpool effect that creates a spiral basin to optimize energy extraction. These characteristics makes it particularly well suited for micro hydropower applications where water resources are scarce, such as small rivers where conventional water turbines underperform. Moreover, the vortex turbine's design utilizes vortex creation for energy extraction, which mitigates the jet interference issues faced by Pelton turbines. Furthermore, vortex turbines often utilize composite materials that reduce susceptibility to corrosion, resulting in lower maintenance needs. Unlike Francis turbines, which can produce vortex ropes and experience significant pressure fluctuations under part load conditions, the vortex turbine operates based on vortex creation in a spiral basin. This mechanism helps stabilize flow and reduce the likelihood of adverse hydraulic effects, leading to a decreased maintenance demands and a prolonged operational life. Furthermore, vortex turbines do not rely on high flow rates to achieve efficient energy conversion, which mitigates issues of cavitation and hydraulic losses associated with Kaplan turbines. The vortex turbine minimizes the risk of cavitation by utilizing vortex dynamics to maintain steady flow conditions. This will lead to fewer mechanical stresses on the vortex turbine components, thus increasing operational lifespan. Regarding ecological considerations, the operational principles of the vortex turbine reduce harmful pressure changes and shear stresses in the water, which can substantially lower risks to aquatic organisms. The nature of vortex flow promotes a more stable pressure environment during operation, thus minimizing disruption to aquatic organisms and allowing most of them to pass through the turbine freely. Next, my groupmate Benito will explain the limitations of the vortex turbine.
Thank you, Wilson. In this section, I would like to talk about a few of the limitations that must be considered when implementing the vortex turbine in Indonesia. There are three limitation categories that I will cover: optimization, scale, and environmental impact. Firstly, despite the large interest over low-head vortex turbine systems, our understanding of the vortex turbine is incomplete, leading to difficulties in optimizing the design for a diverse range of operational conditions. With poor optimization comes lower performance of vortex turbines. The main issue stems from our lack of understanding of the complex vortex dynamics that lead to power generation. These vortex dynamics differ greatly according to the environment, with most of the involved vortexes being turbulent in nature. As such, placing measuring instruments such as probes alters the vortex's flow. Many parametric studies have been conducted on vortex turbines, but they weren't comprehensive, with many having limited ranges, testing in specific conditions, and having a limited number of data points. Studies that are able to provide a similar environment to practical conditions are also rare by nature due to the difficulties in testing in a controlled but extremely varied manner. This can be seen from the significant difference in performance between laboratory testing and practical tests. There are even claims stating that their vortex turbine has reached an efficiency of 85%, but these claims have not been validated. In order to overturn these limitations, more comprehensive research must be conducted in order to gather sufficient data for analysis and design. Numerical optimization methods can also be utilized to supplement experimental studies in any lacking parts. Secondly, I'd like to talk about environmental impact. During regular operations, local river wildlife may enter the turbine. According to Turbulent.be's analysis of fish survival, they had altered their turbine to mitigate harm to wildlife. They had coated their runner blades and exit with thick rubber and added a covering. This was to ensure that blade strikes and scissoring between components would not cut the fish. The blade strikes were also stated to be lower than the maximum threshold of 4.8 meters per second to avoid causing severe damage. Recalculating with the given values, the blade velocity at its tip is about 4 meters per second, confirming their statement. However, while this may be the case with smaller models, such as the one installed in Denver that they used for the study, this study does not consider their larger models, referencing the listed technical specifications on their tech sheet for a 70 kilowatt turbine and calculating with average values, the blade step would actually be 8.45 meters per second. See, this is far greater than the maximum threshold and grants large amounts of concern regarding the wildlife safety. Turbulent.be also provides turbines that provide 90 kilowatts of power, which poses an even greater danger. To solve this, we can restrict the movement of local wildlife and offer them an alternative path. This can be done by placing a mesh net upstream to block the flow of fish and creating a small alternate water flow for wildlife to safely pass through. Alternatively, if the conditions allow for it, the turbine can be placed downstream from a meshed intake channel like a run-of-the-river system, as shown here. Note that in these cases, the civil construction cost would actually be much higher due to the creation of new waterways. Although it should still be noted that the overall environmental impact on fish, as well as other factors such as sediment transportation, are far less affected by vortex turbines than impoundment systems like dams. The last limitation regards the scale that vortex turbines can be used at. Out of the currently published research, none discuss turbines larger than small, with the largest vortex turbine in real use being a model rated for 20 kilowatts of power. This may be because vortex turbines, by nature, have less efficiency compared to other models at large head or large flow rates. However, this is not a problem, as vortex turbines fulfill their own niche in hydropower, this being low head and low flow rate, with a range in between undershot, overshot, and Archimedes screw turbines, of which vortex turbines have a higher efficiency for their specific use case. In the context of Indonesia's small-scale hydropower operations, this is actually optimal, as Indonesia has many smaller streams. And I will now hand it over to my groupmate Wayne.
To implement this form of hydropower, known as hydrovortex, in Indonesia, we need to focus on three key actions. First, local manufacturing. Producing components domestically helps reduce both shipping costs and time, making hydrovortex system easier and more efficient to install. Second, research and development. Continued R&D can further improve turbine efficiency, reduce risk, and overcome technical constraints, making the technology more reliable and productive. Third, government cooperations. We need clear and efficient regulations to ensure the project is approved quickly. The government can also help educate local communities and, in support of Indonesia's sustainability goals, potentially provide funding to accelerate adoption. So, a successful example of this technology is the turbulent hydrovortex turbine installed at Green School, Bali, which can generate up to 15 kilowatts peak. It can supply electricity for 500 people at the school and 4 nearby households. Excess power is shared with the local community. This system has reduced electricity costs up to 60 until 80% and prevents 62 tons of CO2 emissions annually by reducing the reliance on coal. Our main goal is to integrate hydrovortex turbines into a hydro system called waduk. It's a reservoir-based generators. Placing turbines in flowing water may significantly boost energy production. So, with Indonesia's natural potential and proper implementation, hydrovortex turbines can help the country move toward a greener, more sustainable future. That's all. Thank you for listening.